Okay, thank you very much for attending this talk. I know it's late, it's almost the end of the conference, and I promise it will not be a difficult one. It will be actually a review of the cryptography fundamentals and the defaults we have in the Spring framework, as well as in Java in general, because some of them are simply just inherited and they are used from standard Java libraries. If you have questions, please, as I said, feel free to ask them throughout the talk, and at the end I will also take a look in the application to see if you had something there. Let's start. First of all, why it's important to consider security and cryptography in general, which is the topic of our today's talk. Well, because every application is a target, because you manage secrets within your application. There are secrets, there are keys, there are usernames and passwords. There are things that should not be seen by everyone, and you need to manage them securely, because communication over the network is never safe, not even when the communication happens inside your private data center. Even there, things may happen. Even there is a possibility that someone will somehow manage to put their eyes and get their hands on critical data, or at least private data of your clients or users. And of course, that might make you liable or your company. And yes, you've heard me well, even developers in some jurisdictions might be held liable by security issues. So wherever we are, we need to act responsibly, and we need to take care about security in general, and that's the reason for today's talk. And because things happen, these are only a few of the articles I have found quickly throughout the internet from known publications, as Reuters, for example, regarding different things that happened in the past couple of years. And there are many more than this. So yes, things happen, and we live in times where we need to make sure that we keep our systems secure. That's why security, if you ask me, it should be one of the top non-functional requirements you should take care of. I will quickly go over this slide. I'm Laurentiu. Usually people know me for either my YouTube channel or for one of the books that I've wrote. You might get one in paper copy today. If you want, you can follow me on social media. That's how you can find me. 4 points, which are very simple. That's what we discussed today. So it's encryption, either by symmetric or asymmetric keys. It's cryptographic hashing, which we use for passwords and not only. And then I will quickly have a slide on specifications that you need to know. Oh, and all of these are based on a book that my friend Adib here started. And you can raise Adib to say hi. And I will continue. So we work together. We are co-authoring this book. You will see it at the very end. Unfortunately, it's still MIPing. It's still in the early access. So I was not able to bring some copies with me today. Probably I will be able to do that next year when we see each other. But what you will see today, including some of the diagrams here, might actually have been authored by my friend Adib here, not by me. Okay. So yeah, we talk about, first of all, let's start with symmetric encryption. Things are very simple. We encrypt and then we can decrypt. We use only one key. That's why it's called symmetric. And in terms of the most important things you need to remember is that the performance is very good. That's why when we can use symmetric keys, we prefer to use symmetric keys. But we try to avoid using symmetric keys when we need to share keys, because sharing keys can be dangerous. A symmetric key, once it's stolen, it can be used to encrypt the data, so to impersonate the service or the user who should be the only one being able to do that. So that's why we would prefer to have Symmetric for its performance, but we would prefer to do that only when we don't need to share the keys, or if we share them somehow, we need to make sure that this happens only in a secure way. But that's not the only thing we need to know about symmetric key encryption. Important is, what do we actually use? Okay, we use advanced encryption system, which is AES, which happens to be today what we use instead of the old DES that was the preferred one since 1970, if I correctly remember. But how do we use it is also what we want to discuss in the next few minutes of this presentation. However, before continuing with the talk, I added this slide here reminding you about DES, which is a very old algorithm which we do not use anymore, because I want to drag your attention to the fact that cryptographic algorithms change. Why do we care about that? Because we need to always design our architectures in a way in which they should be able to adapt to new algorithms. Yesterday, you might have attended my friend's Anna Maria presentation on quantum cryptography. And if you did so, you have learned that in the very near future, it might be possible to actually adapt our applications to the possibility of the encryption being broken by quantum computers. And it doesn't look like this is possible now, but the reality is that this will happen at some point. You see, DES, in 1970, you would have needed a computer that costed about $250,000 to decrypt DES, which is much more than it means today in terms of money. So it was like saying, well, you need a quantum computer to break it. But that's no longer the case today. One point that you need to remember is, whenever you work on your application, please take care of the architecture. This is something that you always need to make decoupled with interfaces and good abstractions. We do not use interfaces and abstractions everywhere because they overcomplicate our systems. But this is something which should be under abstractions always, so that it allows you to quickly replace it with something new whenever that will be needed. What we discussed today might be or not relevant in a year from now on. We don't know. We can't guess the future. Let's talk about AES and how it works. So I will draw an image of something that represents the most simple mode in which you can apply advanced encryption system. This is called EBC, and as you will learn, we do not use it anymore. But I started with it because it's the easiest and it allows you focus on how it works, especially if you don't know already how that works. As you can see from this hopefully very simple diagram for everyone, the data that needs to be encrypted is split into several blocks, and those blocks are encrypted using a secret key, that symmetric key, that can be used also for decryption. And it results in the encrypting data of concatenated blocks. Very simple, no? In a few terms, this looks very, very digestible. However, this is not what we directly use because it's not really secure, and I will prove now why. Instead, I do recommend you use the third point there, about which we'll discuss progressively, which is called Galois counter mode. Today I will make a comparison between ECB, CBC, and GCM, which are all three modes of applying advanced encryption system. Each of them is better than the other for reasons that we will discuss in simple terms today, because if we would go into complications, we would need to focus on a lot of mathematics, and I don't know about you, but I'm not really in the mood for mathematics, at least at the moment. Can you tell me what animal do you think this is? It's it's a good. It's exactly the animal name I wanted to hear. Exactly. It's the penguin, which is the Linux logo. You identified it correctly. Did everyone identify it? Well, this is exactly why ECB is not something we want to use. This is the Linux logo encrypted using ECB. Okay? Why? Let me tell you why. Any image you take, it will result in something similar. Because what happens here is that if these two blocks of code are the same information, they will give you the same result, which will end into patterns. And our brains, they are designed to recognize patterns. This is exactly one of the tricks that was used many years ago during the Second World War by Turing to decrypt data encrypted by the Enigma machine. Of course, the Enigma machine was not using AES, but it was still the same thing of patterns and things that repeat that helped at the time identify, decrypt data that was encrypted. We don't want that. Yeah, we want to somehow get rid of this this symmetry. By the way, this is called penguin image attack, if you really wanted to know. Let's see how CBC mode from the AES solves that. It uses an initialization vector, and that initialization vector will be different for each of the blocks. Instead of encrypting with the key directly the bytes, it first applies a logical operation between this randomly bytes data called the initialization vector and your data, every time this way resulting in something different. This way, if you try with the same image, because you don't have the symmetry anymore, it will not result anymore into something that you can, let's say, understand from the symmetry that it comes, which is a lot better than the previous mode. It's still not necessarily the safest or the most performant. That's why, in general, we don't use CBC either, and instead we use the Galois counting mode, which is a little bit more complex. It doesn't use blocks at all. It's more a stream-like encryption, where it can encrypt any size of data, and it applies also an authentication tag for each applied data. So it still uses the same idea of having an initialization vector for the logic to eliminate the symmetry. It also creates an authentication tag to stamp somehow that piece of data, and it results into the encrypted data that will always have attached the initialization vector, because you need to reverse that logic you have created, and the authentication tag that tells you that what's here was exactly what was encrypted. So if you put it in, say, a comparison, CBC is like putting all the orange juice cans into a box and encrypting that box, and then if you have multiple boxes of the same size, you take box by box. While this is more like Streamlight, you take each can, and what is missing from here, I asked this is a ChatGPT generated image. I asked it to put me here a stamp. He didn't understand what I want, but you can imagine each can is stamped with an authentication tag. So it's kind of like, you see on the beer cans, it has some kind of aluminum, to avoid that. Because CBC needs that the blocks have the same size, there are situations where you cannot simply just split the data into equal sizes. That's why for ECB and CBC, you will need sometimes to use a padding. So if you hear the concept of a padding The concept of padding means filling the rest of the needed data with some information so that the last block of data has the same length with all the others. Because Galois counting mode doesn't use blocks, it doesn't need a padding either. But you will still have to, in case of Java algorithms, when used from the JDK, you will still have to specify no padding. It's just because you need to put some padding, but it doesn't need. To make a comparison from AES, so Galois counting mode is what we use, and it offers you confidentiality, means encryption, integrity of the data through the authentication tag. It requires an initialization vector because of that, because of for taking out that that symmetry, no, that pattern. It can be parallelizable because it takes unit by unit, and it's, as you can see, the most advantages. So in terms of the nodes, it is the preferred algorithm. You should never use ECB. If you see it anywhere, plan to remove it. And CBC, it's good, okay, but it's a little bit less performant because of the lack of allowing parallelization. And it doesn't have an authentication tag, so it doesn't prove you the integrity of the data. As a note, Spring Security uses Galois counting mode out of the box for the majority of the capabilities where data needs to be stored, like properties, for example, from a vault. Okay, you might not see that. It's defaulted sometimes in the magic behind the scenes, but that's what is used by default. Of course, just to summarize, please, you have a question or?
Since you mentioned it,
yes.
are there some part of the Spring Boot security that doesn't use it, but you can set it as a parameter and change it to GCN?
You can always change what you use in Spring in general. Well, I haven't checked absolutely all the Spring capabilities, but what I know is that Spring is an excellent framework, and an excellent framework always has one very important characteristics. It offers you many things out of the box, because that's the purpose of a framework in general, but at the same time, it offers you always the possibility to customize. And now, thinking about all the things you use in Spring, whether it's security or not, you can always change the implementation. No, it gives you, Spring Boot gives you Hibernate as a default, but you can always use Eclipse Link instead. Spring Boot gives you Tomcat, but you can always use Jetty instead, and so on and so forth. And yes, you will find always possibilities to change also the defaults for the security algorithms. Oh, and by the way, this is a book for you. Congrats. Did I answer the question? Sorry. Yeah? Thank you. Okay, let's go further. So, symmetric encryption. I do recommend you strongly using it for storing things at rest. Whenever you have something and only something that needs the key, that's best when you use symmetric keys. It offers you good performance, but whenever you need to share the keys, then that's problematic. Any way of sharing the keys usually implies an additional risk. And if you can avoid that, then that's best. If we need to secure communication, for example, when we apply encryption or signatures on JWTs for the TLS and any kind of digital signatures in general, then we most likely use asymmetric keys, encryption or signing. In terms of encryption, we have RSA and ECC. My recommendation by the talk of today would be, if possible, you continue with your new implementation to use ECC, which is more performant, but at the same time, RSA is widely used and it's more mature, no? So it's more likely that you will find RSA in many existing systems rather than ECC today. In terms of asymmetric encryption in general, of course, it's exactly the opposite. The key exchange is easy because you only have to exchange what you call the public key, which is called public for a reason. Anyone can see it because it can use it only to make the appropriate operation of checking. But the private key always stays only in one place to whom needs to either sign or decrypt the data. So if we talk about encryption, anyone can encrypt, anyone can mess with the data with the public key, but only the owner of the private key can decrypt. For the signatures is the opposite. Only the owner of the private key is can sign the data, but anyone can validate that the data was signed by whom needed to be signed. And now, as an exercise, a good mathematical exercise, in less than 5 seconds, please give me the prime numbers that multiplied give this. Quick, 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 quick. Two prime numbers. Multiplied. 3 and 7. You own the book very, very well. Wrong. Who said? Give the guy a book. Thank you. Wrong. Okay. The right answer was 61 and 53. This is called a trapdoor function. And it's used by RSA. Okay, and by ECC, but ECC in a different way, we will see it. A trapdoor function means something that is very difficult to reverse. It's very easy to find out that 61 times 53 gives you that number. It's much more difficult to find out the other way around. That's the easiest way, let's say, to describe how RSA works. Okay, in fact, what a trapdoor function works, which is stays behind RSA and ECC. And yeah, of course, it doesn't use 2-digit numbers. It uses large numbers, okay? So RSA does kind of this thing using large prime numbers and uses modular arithmetic to generate keys, which is a field in mathematics I will, again, not go into now because it's not the time for that. It uses this way, it uses the trapdoor one-way functions, which is what I have proven you now. And we use it very commonly for what means communication. Keys are large, however, and this is also the reason why RSA is slower than the next elliptic curve cryptography algorithm, ECC, that we will see on the next slide. Okay. Just a few things about the prime numbers, no, because sometimes when I discuss about this, people ask me, okay, what are some best practice? How does actually RSA choose those numbers? No, because I've randomly choose 2 numbers, fine. It does randomly choose 2 numbers, but they should be large, many digits, and preferably not close to each other. And then there are some mathematics ways of testing that these 2 are secure, which is kind of a bit beyond my mathematical knowledge, but I know it happens somehow in the algorithm. A newer alternative, which is something you should use in case you work on new systems, is elliptic curve cryptography, ECC. And this is an elliptic curve, okay? More precisely, this is an elliptic curve. There are some chosen elliptic curves to be best for applying ECC. You cannot simply just take any mathematical elliptic curve and say, hey, I want to use it. Or you can do that, but it might be insecure. So when ECC is applied, what it actually does, it's very similar to the prime numbers from the RSA. It takes some points randomly at a random given distance on this curve, which is a known curve, which you know the equation of the curve previously. And there are some named curves. I didn't add names here because they have like some strange names that are used and they tested. And if you search, if you will search, you can find what elliptic curve is usually used by WhatsApp to encrypt your messages. What elliptic curve is usually used by some different applications. You usually find them. It's the same thing. It's something you cannot guess. You can imagine this like, you know, a roller coaster. Imagine just taking some random, at a random moment where the train is on a roller coaster, and then taking the points. It's very similar to the random numbers from the RSA. It gives you some randomness, very, very difficult to guess. And this is basically the trapdoor function in terms of ECC. Just that the mathematics behind the scenes make it a little bit more efficient. So, being more efficient because it uses also smaller keys, it makes it ideal for newer systems. It's some kind of the next RSA, if you want. It's like RSA. RSA is still considered secure. ECC is considered secure as well, but ECC is faster. So if you have the possibility to apply it, it's ECC what you would like to apply rather than RSA. However, as I told you, RSA is more mature. We have already discussed, but I want to summarize it in a slide, the fact that you use it for communication in general, okay? So whenever we talk about securing channels, we use preferably asymmetric because it always means, no, we have multiple parties, automatically it means sharing keys. So asymmetric is probably the best choice in this case. But what about passwords? If you work with Spring Security, very often you will use BCrypt. It's actually the default. If you are a little bit more hipstery, you might use Argon 2, which is actually better, but not the default yet, okay? But why do we use this and not simply, I don't know, just encrypting a password? What actually means securing a password? It means storing it in a way in which, even if it's stolen, there are very small chances that someone can find out what exactly the password is. And there are at least two things that we should consider. One of them is that you cannot decrypt the password. And secondly is that if you have the input, you cannot simply just guess the output. You have the output, you cannot guess the input, the other way around. And that's what you could have done, for example, with the old MD5 you might have used like a century ago or something like that. Sorry? SH512. We discussed about that. Good, very good question. Yours. I have that one on a later slide, and I will also explain you why that one shouldn't be used either for storing passwords, okay? For storing passwords, we use one of these two usually, in 99.99% of the cases. And if you had too much tonic, sometimes you use this. No? Yes?
I have a question about RSA. So basically, are we generating the keys from those prime numbers? Because if we are, isn't it theoretically possible to create an algorithm that will try all the possible numbers?
It's possible. That's why watching the talk from Ana Maria yesterday would be a very good choice for you, because you could do that, but with a quantum computer, okay, normally. So somewhere in the future, we might have that, and that's when we will have to use different algorithms for that. By the way, if you didn't see some of the talks that you wanted, because maybe all of them now are good and they are in parallel, you know that they are recorded, so you can see them afterwards as well. So I do recommend you watch that as well. Okay. So if you wanted to know very top of the mountain how BCrypt works, first of all, I think the most important thing, it generates a random piece of data which we call salt, okay? And puts the salt over the thing that it hashes. And it ends up with something like that. This is how it looks like. You've probably seen something like that if you worked with BCrypt. This is the variation of the algorithm. As far as I know, there are about 3 of them now. Adib? 3 of them? I don't remember. I think it was 2A, 2B, and 2Y. No? Yeah. 3 of them, no? Okay. This here is the number of iterations, which is what you give here. Good. This is 10. It would have been 12 for this. Yeah, it would have been 12. So this is the password encoder of 10. 10 would give this. Okay. And then you have the salt, because you need then to be able to, you cannot decrypt a hash, no, because that's the role of a cryptographic hash function, is you can get an output but never get the input, but you should always be able to match an input to an output. So you should have a match function. You should have a mathematical way to say, for this input, this output is identified by this input. So that when you have the thing in the database, someone gives you back the input, you can say, yes, this is the input for which this was produced. But you cannot simply get the input by having only the output, okay? But you need the salt for that. Without the salt, you cannot match. So that's why this is concatenated. Here you would have the value of the salt that was randomly chosen. And of course, at the very end is the hash, the resulted digested data, okay? So this is how we create a password encoder for BCrypt. It's very often used, is the default, by the way. But sometimes you see it in, if you have to override the user detail service bin, then automatically you have to place also the password encoder. So in the majority of the cases, you use this without a parameter, which gives you the default number of iterations, which, to be honest, I don't remember now which that is. Okay, I think it's 10, but I might be wrong. Yes.
Where or how do we store the salt then in a secure way? Because we would still have the salt that we use for the password hash when the user logs in, right?
The salt is concatenated to this, and you don't need to have it like. It's random, of course, and if you see it, it doesn't affect you anyhow, because it's not used to decrypt. You still cannot decrypt even if you have the salt. When the user logs in with the username password, say my secure password 12345, yeah, that 12345 will be matched against the existing string in the database using another mathematical function that uses the salt from this to match that 12345 would give a similar hash using the same number of iterations and the same algorithm.
Okay, so it just has to be similar.
Yes.
Ah, okay.
Yes. So you need this data. They are in your, say you store them in the database. They are in the database, all of them, all the variables you need. The variation of the algorithm, the number of iterations, and the random salt that has been chosen at the first time when the password was encrypted. And then you can rediscover the same value. But you cannot put it back, okay? And a very interesting thing is that it uses this blowfish key extension mechanism, which is something that comes from an algorithm that we do not use anymore. It's a symmetric key algorithm, but we do not use the symmetric key algorithm. We only use what's called inside it the key extension mechanism to create the hash. So it's this BCrypt somehow derived from this blowfish key. So from this blowfish encryption symmetric algorithm that we do not use because it's considered to be insecure, but this part of it that has been used to create the hashing, it's okay, because we create something that you cannot decrypt anymore. Just as a fun fact, and then we have Argon, which is better. It's better. Normally, if you would start now working on a new system, probably you'd like to switch to Argon. The reason why it's better is because it's faster, because it allows also parallelism on multiple threads. So how it does, it actually has multiple lanes that are called. It executes multiple iterations, but every lane can be parallelized, so you can use different threads. As far as I know, they cannot be totally parallelized. At some point, there is some place where depend on one on the other, so there will be some synchronization made there, but still a part of it can be concurrently done. So this can help enhance the performance of the algorithm, making Argon 2 faster a bit than BCrypt. Oh, and by the way, don't you think now that if you put a bigger number here, it will be more secure? Actually, it will be more secure, but there is a big downside. It will be less performant in the term of exponential less performant. I think something like 10 here, if something like 10 here would be, say, solved in 0.0 something seconds, from 0.0 something seconds, if you put 11, there will be something like 0.3 already. So from 0.0 something to 0.3, and if you put 12, it will be already 1 point something. It's a very, it's a very exponential curve, yeah. So don't mess with this. Unless you really know what you do exactly, or if you do mess with this, be sure you test it properly and make sure that your system works behaves as you want it to behave, because you will compromise a lot of performance. And then your question would be, does that make sense? What does it help me for? Yes.
One question. You assume that this stuff all happens in the backend. So if a user types in his password in my website, how do I get into the backend without, with it still being secure?
Using TLS, HTTPS.
Okay.
Yeah.
That's enough?
Yeah, that's what we do now. So you don't have to like encrypt it somehow on the front end or stuff like that. I don't know anyone like really doing that, honestly. And yes.
The length of the hash is always 31.
Yes, yes. Yeah, it will always get you the same length of the output with this. Very good question, actually. The last book is yours. And I gave the books again not based on the questions are good or they are not things like good or bad questions. I just gave them randomly and that's it, okay? Just to apologize for you guys who didn't get like all the other 99.99% of the class here. Going back to Argon, so you'll have a little bit more parameters here because it's also more customizable. By the way, it works on filling based on the input and some randomly pseudo-random generated data, a piece of memory, and this let's say a block of memory or a buffer of memory, I think they call it sometimes, this is the default, which is about 64 megabytes. No, I think these are all of them the defaults in Spring Security. Except this one, I think it's only 2 iterations, the default. So if you use it without parameters in Spring Security, it will be 2 there as iterations. But all of the parameters can be changed. So because it allows parallelism, you can use concurrency according to the system on which you know this will run, and customize this way for performance enhancement, because that's basically what you usually want to do when you change those parameters there. So you have some defaults from Spring, but you want to enhance them. So Argon 2, which is now the, say, prodigy baby of hash functions for passwords, has won the password hashing competition in 2015, which is about 10 years ago already. And at the moment is considered to be the best in terms of hashing for passwords. And now, of course, we had the question already from the class about SHA. Why is not SHA on your list? Well, it is. But you should never use it for password hashing. Okay? Why? All the others that I have presented have an exponential curve for latency for a reason. They have been created on purpose for that. So that is difficult to apply brute force attacks over them. SHA doesn't have that. SHA is something that we use for data integrity. So creating a hash over something so that you can check the hash and validate the data is still integer. Who does that on a daily basis? What tool that you use does that on a daily basis? Git, very good. Git, I don't have a book anymore, sorry. Git, Maven, or anything that downloads jar files or something? No? So we use that. Unfortunately, did you know that Git uses an old unaccepted version of SHA? Exactly. Git uses that. It will change that probably, but I think it's a little bit more difficult to change it. That's why they didn't do that. By the way, I've learned that from Adib, okay, from the book, just for you to know. Normally, today we should use either SHA-2 or SHA-3. Both of them are okay. Theoretically, SHA-3 is a bit better. Practically, it doesn't really matter. We use one or the other, but very, very, very careful if you use them with the security module in Java. Oh, I'm okay with the time. Sorry for that. I'm just checking. Okay, almost there. If you use it with the security API from Java, SHA-1, okay, is SHA minus 1. SHA-2 is SHA minus 256 or 512 or any other version like that. They both start with SHA, okay? If you want to use SHA-3, it's SHA-3 minus something. The first two might put you in difficulty because you would say, hey, I use SHA-256. Does that mean I'm using SHA-1? No, in that case, you're actually using SHA-2, which is good, okay? But that's how they were named. And to end my discussion, I would like to just draw your attention on the fact that besides the cryptography itself, which we know, algorithms that we know we need to use and everything, there are a few essential specifications. I would like you to remember them and to know that this is what you should know. I will not talk about each and every one of them now. They are just enumerated there, and this is what the developer normally should be aware of in terms of security. So they do use and refer to all the cryptography that we have discussed today behind the scenes, but all of them, they put them in a different topic. Now, Jose is the specification describing how token encryption and signing should work. Nimbus is an implementation of Jose, for example. You are probably using Nimbus on a daily basis if you use JVTs with Spring. No? OAuth 2 is the specification for the authorization framework. OpenID Connect is a protocol for identity addition of the login layer over OAuth 2. JVT defines the token format for JSON Web Token. Pixie is a way to enhance OAuth 2 flows by securing public clients, and of course TLS, which ensures the securing of the communications. So keep them, yes, please.
I have a use case where I have to share a password, or rather, currently what I do is I generate a UUID that gets distributed to the customers via a QR code.
Okay.
Is there any way to make it more secure that it's just not a UUID?
So just to recap, you have a UUID you randomly generate, but you want to share it with someone. You, however, want to make this secret in a way or another.
Yeah.
I would recommend you in advance exchange some asymmetric keys, because it's some exchange communication. The first recommendation would be asymmetric keys, so that one would be able to encrypt and the other will be able to decrypt this. So instead of using only the TLS, you would rely also on your own encryption.
There's no real. It's just like a QR code, and that's it. That's the first and last code.
If you consider that a secret and you want to encrypt it, you have only two possibilities: symmetric keys or asymmetric keys. When it comes to communication, especially if the two entities discussing are not related one to the other, are part of the same, say, system and the organization, then it should only be asymmetric keys.
It's more like the consumer and the consumer and the server, and having it's just about authorization. Like, can they access that?
This is your choice. I can't tell you more than this. This is your choice. The second would be, yeah, go on. No, the second would be symmetric keys, and that's the compromise that you can make.
Because I want to go back again to the asymmetric key, because you mentioned that the RSA is a little bit more mature than
Yes,
the
a little bit more,
yeah,
more mature.
The thing is, now that we are moving to another authorization server, we have actually the chance to choose which algorithm we can use.
Then use ECC. If you have this chance, then yes, you can now go to ECC. But if you don't, you are not in a situation where you should or you can change it by the means. It's not something. It's not a rush. You shouldn't like tomorrow now go to work and say, hey, I've learned that talk that we should now change to ECC. Okay, don't do that because it's not needed. Okay, but if you can, if you have a new system or you are in a situation where you can do that, then most likely is best to take this opportunity, we will say, and use ECC. And before ending completely with my talk, this was the book I was talking about. Adib started it, I tried to finish it, we worked together on it and put a lot more than you've heard here, of course, in a 40 minutes talk or 50 minutes talk. You now find it only in early access on Manning, but very soon will be lists of security for developers with examples in Java and Spring. And with that being said, thank you very much, everyone. And I have only one question here, okay, but you can ask others. What is your experience with post-quantum encryption? Exactly what I've learned yesterday from Anna Maria. I hope that answers the question. Are there any other questions that you want me to address?
Argon was not adopted, I didn't get it, so it's already there.
It's not yet adopted. Like any other technology, it takes time sometimes to adopt it. It's not like it always you always just change that from one day to another, because you see, BCrypt is still very good. So why should I change it just because, of course, it's better in terms of performance, but still, we didn't say we will quit using BCrypt, no? It's still a good algorithm, so we'll continue using it. Not enough, exactly. Not enough reasons, to change it. Okay? 64 megabytes is the default, yes, for memory buffer. Yes, yes.
Sounds like a reason why it might not be the same.
Can be, yeah, but yeah, can be. Cool. You can even actually, it's designed for larger than that. So that's I think the minimum or just the default, but you can use larger, just as a fact. Yeah, sure, go on.
I have a question about BCrypt. As I remember, it's possible that when you receive like two different hash functions, like when you apply this password encoded, you can compare hash functions despite the fact that they have different salts. Is it true?
I'm not sure if I understood, but the salt is used to eliminate what we call rainbow tables. So take MD5. Always, if you have the password 12345, you will always get the output ABCD. I don't know. Yeah. Then, if you put them in a database, in a Postgres database, on a column you have the input, and on the column you have the output, you can suddenly search for the output and find the input. So you cannot decrypt, but you can simply store in advance 1 million passwords and their outputs, and you can then search by the output and find the input, and that's a rainbow table. Because you apply a salt, then this is already no more possible, because 1, 2, 3, 4, 5 might give you ABCD, but it also can give you X, Y, Z, Q. Okay?
But my question is about if I apply the BCrypt function to the password, and I have it stored in database as well. Sure, they have different salts.
Of course.
It's possible
Yes.
to compare just the result of the function, or I still need the plain password in order to do the comparison.
You only need the salt because BCrypt is hashing. It doesn't have a secure key. It only has the salt, and the salt is stored within the output. Actually, it's that format now is the algorithm, the salt, and then the hash. So what it does, it splits them apart. It's actually also the iterations, no? And it says, hey, I have to use 2A, 10 iterations with this random salt, and this is the hash. And this is everything the matching algorithm needs to validate that the password is what it is. But of course, the same 1, 2, 3, 4, 5 can have an infinite number of outputs this way. This first can have 2A, 10, 1 random salt, 1 hash. The other, for the same input you can have 2A, still 10 because you have 10 iterations, then another salt, another hash. And you can even have 2B because you used another variation, and another number of iterations, another salt, another. So you can have basically an infinite number of outputs for the same input.
But it's possible to compare them, or in order to compare,
you need to run the algorithm. What to compare? Because the salt is random, the hash will be generated based on the random salt. So.
But for example, I have it stored in database. Now, in order to verify the password, I need to get the previous result, then apply the same salt using the same number of iterations.
Yes.
And the same.
Correct. Correct. And you can, yeah, exactly. And that's how you find if it was or not the same. Yes.
I have one question about the SHA-1, like SHA-1.
SHA-1.
Problem is it that they found collisions?
Collisions, exactly. Collisions are the problem with SHA. So in terms of the amount of data, the number of collisions that happens on SHA-1 is not considered acceptable anymore.
Because
exactly.
for 2 there are no collisions found so far as I know.
Are they netos, Adib? Can you?
If there was, you'd have heard about it.
Probably, yeah.
Because I know for AMD4, I think you can download tables for.
Oh, clearly. That was like when these dinosaurs still ruled the earth. Okay, I think I can put this down now.